So today I'm going to be showing you problem number 25 on page 188. It's a moving ladder problem, and the problem states, a ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. Now since this problem has 3 parts, we're going to start off with part A. Part A says, how fast is the top of the ladder moving down the wall when its base is 7 feet, 15 feet, and 24 feet from the wall? So the first thing you're going to want to do is draw a diagram of what's actually going on in this problem. We're going to call the wall of the house R, the ground, or the base, X. We're going to call the ladder 25 feet because that's what was given to us in the problem. The ladder doesn't get a variable because its length is never changing, it's a constant. And the rate at which the base of the ladder is being pulled was also given, and it was 2 feet per second. After you draw the diagram, you're going to want to list your givens because you're going to need them later in the problem. So we obviously have dx dt, the rate at which the ladder is getting pulled, is 2 feet per second. And we're trying to find how fast the top of the ladder is moving down the wall, which is r, which then turns into dr dt when we're trying to find it as a rate. And our 3 different variables for x are going to be 7 feet, 15 feet, and 24 feet. So now what you're going to want to do is try to think of an equation that's going to generate all your variables once the derivative is taken. In this case, we're going to use the Pythagorean theorem. So the Pythagorean theorem is a squared plus b squared equals c squared, but we're going to use the variables that are given to us in the problem. So in this case, we have x squared plus r squared equals 25 squared. And when you simplify that, you just simply get x squared plus r squared equals 625. After you simplify, we're going to implicitly differentiate with respect to time. So that means when we take the derivative, we're going to end up kicking out a dx dt and a dr dt. In this case, when we take the derivative, it's going to be 2x dx dt plus 2r dr dt, and we know that the derivative of a constant is 0. Now we're going to try to isolate dr dt as best as we can for the moment, so we're going to take 2r dr dt and subtract it over to the right side. So then we get 2x dx dt is equal to negative 2r dr dt. And this is what we're going to use to find out what dr dt is. So right now, we're going to try to find dr dt when x is equal to 7 feet. But what we realize is that instead of only having one variable, which is supposed to be dr dt, we have 2 variables. We know what x is because that's 7 feet. We know what dx dt is because it was given, but we don't have r or dr dt. And since we're trying to solve for dr dt, we need to know what r is in order to figure it out. So you need to think to yourself, how am I going to solve for r? And you're going to want to use the Pythagorean theorem again. But in this case, we know what x is. So we're going to do 7 squared, which is our base, plus r squared, because we're trying to solve for r, is equal to 625, which is 25 squared. And when you simplify all that, you're going to get r squared. R squared is equal to 576. Take the square root of both sides, and you end up getting r is equal to plus or minus 24 feet. Now that you have r, we can plug in to our derivative and solve for dr dt. So basically from here on out, it's just plug and chug. So you have 2 times 7 feet, because that's our variable in this case, times 2 feet per second, because that's our dx dt, is equal to negative 2, r, which is what we solved for, 24 feet, and then dr dt is our variable. So this side is going to end up equaling 28 feet squared per second, and this side's going to be negative 48 feet dr dt. And then you're just going to divide and get dr dt by itself. And you end up getting that dr dt is equal to negative 0.583 feet per second. That was easy, wasn't it? And all you're going to do is do the same thing for the other two variables, x at 15 feet and x at 24 feet. So now that we know how to do it, we're just going to do this real quick, and we're just going to do x equals 15 feet. When you solve for r, when you do this process, you end up getting its r value being plus or minus 20 feet. And when you end up plugging and chugging, you end up dr dt being negative 1.5 feet per second. And the same setup for 24 feet. Your r value ends up being plus or minus 7 feet. And our dr dt ends up being negative 6.86 feet per second. So now we're going to move on to part B. And part B says, find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So since we already solved for dr dt at x equals 7 feet, we know that our given is negative 0.583 feet per second for dr dt at 7 feet being our base. We also know from the first part of the problem that dx dt, which was given, is 2 feet per second. And when we solved for r in order to find dr dt in part A, we found that it was 24 feet. And r is the side of the wall. So now since we're trying to find the rate at which the area of the triangle is changing, we know that we're going to use the area formula. And the area formula is A equals 1/2 base times height. Or if we use the variables from our problem, we're going to do half times x times r. So we're going to want to take the derivative with respect to time again. So we know that A is equal to 1/2 x times r. So when we take the derivative, we get dA dt is equal to 1/2. This is going to be a constant multiplier. It's just going to tag along as we do the derivative. And since we have x times r and it's just not plain old x, we know that we have to do the product rule. And the product rule is first d second plus second d first. So we take the first times the derivative of the second, which is dr dt, plus second times the derivative of the first. And there we have dA dt is equal to 1/2 times x dr dt plus r dx dt. And since we're solving for dA dt and it's already isolated, from here on out we can just plug in all the information we have and solve for dA dt. So we have dA dt is equal to 1/2. Our x in this case is 7. We know our dr dt from already solving it is negative 0.583 plus r, which we solved for in the first part, is 24 times dx dt, which is still 2. And then we have dA dt is equal to 1/2. 7 times negative 0.583 is negative 4.08. And we're going to add in our units here. So right now we have feet squared over seconds plus 24 times 4 is 48. Also feet squared per second. And when you add those two together, you get 43 0.92 feet squared per second. And then finally, once we distribute our 1/2, we get our final answer, which is dA dt equals 21.96 feet squared per second. Our units are in feet squared per second because we're solving for area, which is always squared. And there you have it. The rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall is 21.96 feet squared per second. So finally, we're on the last step of our problem, which is part C. And part C says, find the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall. So what we're going to do is still bring over all the information that we found out from the beginning when x equals 7 feet. So we're going to bring our dr dt over, which is still negative 0.583 feet per second when the base is 7 feet. We know dx dt is always 2 feet per second. And we know that when we solve for r, when x is 7 feet, we got 24 feet, and that's the side of the wall. And since we're trying to find the rate at which the angle between the ladder and the wall of the house is changing, that's going to be d theta dt. Now we're going to have to generate an equation that's going to help us find d theta dt. And we're going to have to make a SOHCAHTOA decision in this case. We have r, but we know x is changing, so x is going to remain a variable for now. And we'll also use 25 feet. Since we're using the opposite angle over the hypotenuse, we're going to use sine theta. So, sine theta is equal to x over 25 feet. And this is the equation we're going to take the derivative of. So when we take the derivative with respect to time, we get that the derivative of sine is cosine d theta dt, and since we have x over 25, we're going to take out 1 over 25, and that's going to remain a constant multiplier till the very end. It just makes taking the derivative a lot easier. So now we're left with x, but that x turns into dx dt. Now when we look at this, we have to say, do we have all of our variables besides d theta dt, since that we're solving for? Well, we know dx dt because it's always been the same, 2 feet per second. We're solving for d theta dt, but we don't have theta. So what are we going to do? Well, we're going to use our original equation, but since we know that the base of the ladder is 7 feet from the wall, we're going to just plug 7 into x to find theta. So we have sine of theta is equal to 7 feet over 25 feet. And you get that that is equal to 0.28. And that's going to be what theta is equal to. And you just find that by simply plugging that in your calculator. So now we're ready to substitute and figure out d theta dt when the ladder is 7 feet from the wall. So we're just going to substitute into our derivative. We have cosine of theta, which we figured out was 0.28, d theta dt, which is what we're going to solve for, so we're going to keep that a variable, 1 over 25, which is our constant multiplier, and we know dx dt is 2 feet per second. So cosine of 0.28 when plugged into the calculator is 0.96 d theta dt, which is equal to 0.08 feet per second, because all you're going to do is distribute that to the 2. And then you're going to divide by 0.96 on both sides in order to get d theta dt by yourself. And we get that our final answer is 0.83 radians per second. And that 0.83 is the rate at which the angle between the ladder and the wall of the house is changing when the base of the ladder is 7 feet from the wall.